Ich würde gerne die Evaluation mit Ihnen besprechen, umso mehr, dass sie für mich völlig neue Erfahrung positiv ausgefallen ist. Sie sehen also, dass Sie doch anscheinend ganz zufrieden mit der Vorlesung sind. Hier diesen Punkt, da müssen wir mal drauf eingehen, das ist aber nach meinem Dafürhalten ein Defekt im Fragebogen. Wir können uns das jetzt gern im Detail anschauen. Ich glaube, es gibt eigentlich da aber auch relativ wenig jetzt zu diskutieren. Okay, also anscheinend haben sich alle Gruppen beteiligt, auch die CE-Studierenden. Die die Zahlen, die Sie so für den Arbeitsaufwand angeben, die scheinen mir im Mittel so angemessen zu sein. Also ja, 1 bis 2 für die Nachbereitung kommt mir fast ein bisschen wenig vor, würde für mich nicht ausreichen. Aber so 3 bis 5 ist vielleicht ein ganz vernünftiger Mittelwert und auch für die Übungen als Mittelwert oder als häufiger Wert 5 bis 6 vielleicht ganz angemessen. Ja, diese Zahlen, die sind jetzt, wie gesagt, völlig neue Erfahrung für mich, einigermaßen positiv. Die Anfänger sehen das immer ganz anders, die meinen immer alle, dass ich überhaupt keine Ahnung von Mathematik habe. Okay, ich weiß nicht, wer Sie da beeinflusst hat, das anders zu sehen. Ja, sind die Ausführungen hinreichend detailliert? Da fällt das ein bisschen ab. Ja, ich versuche schon, das ein bisschen, wir haben ja hier eine gewisse Balance zu machen zwischen den Bedürfnissen der CE-Studenten und der Mathematikstudenten. And I try to keep this balance on the one hand side, having a lot of, to my impression, a lot of heuristic explanation also in the lecture. But of course, I also have to keep a sort of a minimum of mathematics in the whole thing. So my suggestion would be, let me put it another way. Some proofs, and I think this is quite reasonable, it's not necessary that one has to go through every proof and of every lemma which is encountered somewhere. That is my point of view. But it also means, in particular for the mathematics students, that would be my suggestion, that at those places where I do things only sketchy or omit parts, that would be, of course, then an occasion to see how far these things are understood and then also to try to it's not my idea, that's maybe one can do this or one has to do this for engineering courses, is to do one example after the other. I think this is a type of knowledge which is a sort of outdated, it's anachronistic. We have all kinds of advanced software nowadays, which are, in the old days, there was hardly no canned software available, and if it was so, it was rubbish. Unfortunately, in terms of numerical mathematics, unfortunately, it's not the case anymore. There's good software, it is more or less state-of-the-art, a little bit less maybe, but nevertheless one can use it, and a lot of engineers are using it. If you break yourself down to the user of software, you're in a competition with everybody. Everybody can use software, and everybody can produce a colorful picture and say, oh, this looks very nice, this is reality. But maybe it's totally nonsense what you got out. And my idea is here to learn the foundations to really to be able to judge, is this reasonable what I got there? Okay, and that means, of course, that we have to go a little bit more into function analysis and things like that. Okay. Okay, concerning the exercises, I suggest you should discuss this in the exercises, in particular your comments, in particular also those comments with regard to MATLAB. I don't want to say too much about this issue here. The only point is, of course, it should be so that if you do your exercises with, let's say, Octave or with Scilab, then it should be feasible. I have told Mr. Elbinger again that he has to make sure that it works in the same way in these clones. All the other arguments concerning open source software and so on, yeah, okay, what shall I say? I'm also a computer scientist by training. Also, this is a long time ago. And I spent my youth in programming a PDP-11 in assembler instead of sitting at the park bench in the summer. But maybe it was a mistake. So I think I know what I'm talking about. But I think this open source issue is just, yeah, it's non-realistic. If you go and get your driver's license, you also do not ask for an open source car. It's by BMW or whatsoever. Anyway, but you can discuss this in the exercises, but let it turn the argument around. What I said, if you look at a tool like MATLAB, everybody now can use that, or if you cannot use that efficiently, you are somebody like who has not a driver's license. It's like reading and writing. It's a basic cultural tool. Okay, everything concerning the exercises. Furthermore, I would like to. You can and you should discuss this more in detail in the exercises with regard to the comments concerning the contents and the presentation. There was one comment which I did not understand concerning the use of direct and iterative solvers, but we will come to this issue again. And there were comments concerning the use of the slides. I see the problems in using the slides, and usually I do it in a mixed fashion, that I do the proofs on the blackboard. I have to admit I'm a little bit spoiled by these slides here because they contain the proofs already. And then, of course, I'm spoiled in doing the proofs on the basis of the slides, which saves me some time. Otherwise, I would not be able to cover all these needs and go through these different aspects. So I will keep this in mind and try not to overdo it. So, wo sind wir jetzt? So let's continue. We are more or less finished with the discussion. Here, the transparencies. With the discussion of the of our first attempt to the finite element theory. And the last point we are now talking about is the possibility of a maximum principle. And we deal with the maximum principle purely in an algebraic version, in the sense that we say, we have seen already, in the end we are solving a linear set of equations, and we have seen if the matrix of, so to speak, the stiffness matrix plus the part which which brings in the contribution of the Dirichlet boundary conditions and of the inhomogeneous boundary conditions. If this matrix has certain properties, then on the discrete level there is a maximum principle in various versions, which in all versions means that there is comparison, which is very important because comparison means means a lot of things. It means uniqueness of the solutions. It means that we can get bounds for the solution by finding upper solutions and lower solutions. And as we have seen also in the finite difference context, it also gives a mean to do in the finite difference context an order of convergence estimate, because it gives us then stability in the L infinity norm. when we now in the finite element context prove a maximum principle or prove these properties of the matrix, that is that the matrix is an inverse monotone matrix, and we do so by showing that's a specific inverse monotone matrix, an M matrix, so a matrix with a certain sign structure, then we could also build an order of convergence estimate on this. But that would mean that we would have to do a consistency error estimate in the corresponding discrete L infinity norm. One can do so. I'm not going to do that here. One could do so, but at least if one do it more or less directly, then we get a decrease in order. So in the situations which we are now going to identify and have more or less already identified, where a maximum principle is valid, for this specific situation we are looking at, namely 2D, triangles, linear ansatz, then there is also a discrete L infinity estimate, but only proven in this way to the order of h, not h square, what we would like to see. In fact, there is an h square or h squared times a logarithmic term estimate, but this requires different techniques. So this is not the issue here. The issue is really just to see the maximum principle. And first of all, we would like to see that we have the chance that the discretization matrix is an M matrix, and that is the specific sign structure which we need, which in particular says the off-diagonal elements have to be non-positive. So we started in looking at the off-diagonal elements, and we have seen if we can prove the following lemma. Where is it? Here, which tells us what is the contribution of one element to such an off-diagonal entry. Then we can get a representation for the total off-diagonal element, which just consists either of this one element, of the contribution of this one element, if this is a boundary element, or of the two elements which have the edge in common to which these nodes I and j belong. And then we have seen already, if this lemma is true, the condition which assures us this non-positivity property is the one that, so the strong requirement would be the angle opposite to this edge of the triangle is less or equal to pi half. That applies for the boundary element. And if we have two elements meeting in this edge, we can relax this condition by saying the sum of the two angles, which are opposite in the corresponding triangles to this corresponding edge, is less than pi, less or equal to pi. That means we can allow for one obtuse angle if the other angle is small enough. Okay, so we have to check this lemma, which tells us that we can represent this contribution by -1/2 times the cosine of the interior angle opposite to this edge with the vertices, with the nodes AI and AJ. So let's look at the situation. So maybe we go to this picture and I freeze it. No, come on. Okay, so we have some picture in mind. So this should be the situation. So we have here our two, okay, I should have done it the other way around. We have our two points A1 and AJ. We have the angle, the opposite angle, alpha ij, and the further notations are the unit outer normals at the edges of the element, nu ki and nu jk correspondingly, and the height hj. So, and with these quantities we now want to express what's happening. So we have to look at the functions phi I and phi j, more precisely at their gradients. And what is the situation? So if we look at phi j is opposite, is 0 at the whole edge opposite to AJ. That means the gradient, which points in the direction of strongest increase of every differential function, the gradient is oriented in the direction of the normal. So we have the following relation, but it's oppositely directed, because the gradient is the function is going down from 1 to 0, and so the gradient would point inward, and the outer normal is pointing outward. So first of all, we have this relation here. We know that the gradient is proportional to the negative outer normal, and the proportionality factor, of course, is just the Euclidean norm. If I put here an alpha and I put the Euclidean norm on it, I see because this has norm 1, that it has to be this factor here. So the only thing what we now have to do is to compute this quantity here. Okay. In general, we have this relation here, because the length of the unit normal is 0. So what we have to do is to compute this derivatives, we have to compute a directional derivative. So what is written here is up to the minus sign is the directional derivative in the direction of the outer normal, or it's the directional derivative in the direction of the inner normal, what we have here. Okay, so let's do that. So to compute a directional derivative, we are talking about linear functions here. We can do this exactly by a difference quotient. So we just need 2 points, need the values at these points, and we need the length of the connecting line. So we go along the height here. This is the direction we are looking at. Here we have the value 1. Here we have the value here we have the value 1, here we have the value 0. So we have 0 minus 1 divided by hj. So this is the quantity, and with the corresponding sign, then we plug this in, we get this relation here. Okay, with this we have the similar relation, of course, we have for the index I here. And then this normal comes into play with the normal Vjk. So we can have now a formula for the product. This is our constant integrand in this integral we are going to compute. So we have to say something about this quantity. Okay, now we have those 2 normals. Here, but this can be expressed as every scalar product in every Euclidean scalar product as the length of the vectors. Okay, this is 1 in both cases, times the cosine of the included vector, the cosine of the included angle. So if we look at the angle, so yeah, I should. Unfortunately, I cannot go to this side with a pointer, but maybe I can. Okay, so look at this quadrangle here. Then you see we have 2 right angles. I hope you can see what I mean. Then we have 2 right angles, and this just means this angle we are talking about between these normals is just pi minus alpha, and therefore we have just here the change in the sign. So the cosine of the angle we are talking about is minus the cosine of the angle alpha. Okay, so that is our first formula, so let's go on. So what is this here? This is just the area formula for a triangle. 2 times the area is height times corresponding edge length. And we can write this down for this edge here, and we can write it down for this edge here. Now it's really okay. So we get this. So we get, maybe I don't need this anymore. So we get these 2 formulas, this one and this one. And okay, and now we need a formula for the height, but this we know already, this is the sine times the other edge. This is just sine is, sinus ist Gegenkathete durch Hypotenuse. Sine is opposite leg divided by hypotenuse. I'm now extremely fit again in these things. I know everything about the sine theorem and the cosine theorem because my daughter is now in the 10th grade. And of course, that is what you're doing there. Okay, so we have these equalities here. So let's see what we can do with that. So we start with this relation here. We plug in, so on the basis of what we have here, we get this relation. So plug in one of these relations here, then the corresponding terms cancel, and then we go back to this form here. So we have this form here. And finally, here for this term, we use now, and for together with one of the k's here, we use one of these, we use this relation, so we lose one of the k's here, we get a sine in, so we have cosine over sine, so we get really a cotangent. Okay, this is really elementary computation, you have just to plug it in and see this, that this adds now, with this you have to take care of the 2, therefore the 4 becomes a 2 here, and so on, and you see this is exactly the formula we have claimed that it holds. Okay, and by this, now we have more or less done the most complicated step, or maybe not the most complicated, but the one we are talking about, step here in conjunction with the properties of the M matrix properties of the stiffness matrix, and maybe to remind you what we really have to, what is the total amount of properties we have to look at. We go back a long time. Was ist jetzt los? Oh, Marke, das ist nicht. And see that I find the sequence of conditions which we had, which is here denoted by 128 and in the English edition by 132. Wo ist es denn jetzt? Here we go. Here are the sequence of conditions. So that was the one formulation. And let's go through for a moment. What do we have to see? Okay, here this one is elementary, that the diagonal elements are positive. That is clear. We integrate about a non-negative function which is not 0. This is the crucial condition with the non-positivity of the off-diagonal elements, both in the matrix, in the degrees of freedom dealing with the non-Dirichlet degrees of freedom, and also in this matrix AH hat dealing with the Dirichlet boundary conditions. So this we have checked now. We have found a condition which assures us this property. And what are the further conditions? One is that the sum over over each row has to be non-negative. That also applies to the full matrix. This AH tilde is now the full rectangular matrix, including the AH hat. there is a slight condition saying that in this AH hat matrix, each degree of freedom has really been be active, be influencing the solution. And then there's one crucial condition which is difficult to satisfy, and in some cases is not possible to satisfy. This is the irreducibility of the matrix. And because of this critical condition, we have formulated a variant of those conditions, which is given here, where we on the one hand side have enhanced a little bit the requirements. Namely, we said if we look at the large, at the not square, the rectangular matrix, including the Dirichlet part, we would like to have that the sum over the row is not only non-negative, but it has to be 0. That is the enhancement of the conditions, and we can relax the irreducibility condition in the sense that we can say we only have to look at those nodes where the sum equal to 0 for the square matrix is fulfilled. So that means, if you remember the derivation, that means these are the degrees of freedom which are not close to the boundary, which do not have Dirichlet nodes, so to speak, in their stencil, in their neighborhood. Those we have to be able to connect those, let's say, interior points to a point which has the condition with strictly positive here. So that would correspond to a point which has Dirichlet nodes in its neighborhood. So by this elimination process, so to speak, from the sum equals to 0, a negative part goes away, and therefore a positive sum remains. And connecting means that we find a sequence of indices that, stepping along these connecting points, we always have an entry in the matrix. We never step at a 0. That corresponds to the situation if we you have discussed this, I think, what is the relation between irreducibility and a corresponding graph. If we attribute a graph to the matrix in the sense that we have, if the matrix is in this case an M1, we have as many nodes as we have dimensions in the matrix, and there is a connecting edge in the graph from I to j if aij is non-equal to 0. So in this sense, if we look at this corresponding adjacency graph, as it is called, then that means we can move along. We can move in this adjacency graph. We can move from a point which is in the interior, in this sense, to a point which is close to the boundary. And irreducibility would mean we can move from every point to every point. So in this sense, this is a relaxation of the irreducibility condition. Okay. Let's freeze this variant here. Now I do it the other way around. And let's go back. And let's see what we have to do with this, with the further conditions. Okay, so this was then the full formula we discussed already last time, which gave us this angle condition we already discussed, which is here denoted again. And we need a further condition, which is a pure theoretical condition. It says the discretization must be like that for any pair of nodes which belong to omega union with gamma 1, gamma 2. So these are all the nodes excluding the Dirichlet nodes. If I have any two of these nodes, I must be able to connect these two nodes with a polygon along of edges of triangles and the vertices which I touch in this process also have to belong to this set. That's a pure geometrical condition for the triangulation. It doesn't, for the connectivity of the triangulation, it does not yet say anything about the corresponding contribution in the matrix. And this is also a little bit of a problem which still has to be solved. So geometrically, this just means that can phrase it differently. You can either say it's not allowed that the domain becomes very thin at some place, or put it the other way around. If it is thin at some place, the triangulation must be fine enough to cope with that. So this situation is not allowed because, for example, if I take this node and this node, I have no chance to go along edges because here in this thin channel here, I have no interior node through which I can pass. So this is only tells us the discretization should not be unnaturally coarse. So in this, because otherwise this would just mean these two sets are disconnected, and then of course you cannot have a maximum principle because these both parts can act then independently on the discrete level. So now let's go through the conditions on the left-hand side. The claim is 1 is okay, 2 is okay, this we have dealt with. 5 is okay, this was the situation we dealt with. And 6 is also okay. 6 star. 6 star tells us that the sum has to be 0. Why is this? Wondering there's no indication about that. Here's the proof for 6 star. So 6 star said if I take the full matrix, the rectangular matrix, then the sum over the full row has to be 0. Why is this the case? So I have to sum over all those elements. So I bring the sum here in. So I sum over all nodes, including the Dirichlet nodes, and I have here the sum over the nodal basis functions, and I can think of a 1 in front of that. That means what I have here is the interpolant of the constant function 1. But the interpolant of the constant 1 is, of course, the 1, so I have a 1, exactly 1 here, so the gradient is 0, and therefore I have a 0 here. The reason for that is I really have to, the point is really I have to, the constant 1 has to be in my space. That would not be true if I sum here only about the matrix AH, because then I would have, in the case of Dirichlet boundary conditions, because then the constant 1 would not be allowed, because it's not 0 at the Dirichlet boundary part. So either I go over all nodes here, or I am in a situation which then in the end is the same, where no Dirichlet boundary conditions appear. So, but if I have this situation, then of course I have at least the sign situation for the sum of the square matrix, because the part which I subtract here is a non-positive part. This we have seen already. So we have the condition 6 star, and we have seen the condition 3. This is a little bit redundantly formulated, but now the problem is with the corresponding condition 4 star. And the problem is our connectivity condition tells us we can find a path through the graph, and no, you have to put it the other way around. We can find a path through the triangulation. That was just a condition. But this does not yet tell us that this is a path through the graph, because an edge in the triangulation only becomes an edge in the graph if the corresponding Aij is non-zero. And this is not yet guaranteed. And this is a tricky part of the proof. And in our good tradition, omitting all the difficult things, we will omit it. But we should be aware of this problem. So one has to find out, one has to make sure that that it's possible to find at least one of these connections through the edges of the triangulations, which is also a path in the sense of the graph, of the adjacency graph. And if one does so, one has in particular also checked the condition 7 here. One can, if one is not so ambitious and has a more strict requirement, saying, for example, if we would say all our angles are less, this is quite a restriction, are less than pi half, then we are sure that all contributions are negative. The positive contributions appear for one specific element. If you only look at the elements individually, we have seen if one of the angles is a right angle. But if we are very strict and say all angles are strictly acute, then all the contributions are strictly negative, and then all these problems do not appear. Okay. That is basically what is said here. Yeah, and the next thing what we have to know, and that is also very specific for piecewise linears, and it's wrong already if you look at piecewise quadratics, that the maximum of the corresponding piecewise function, because at each of the elements, for each of the planes we are looking at, then we used this argument already, the maximum is attained at the extremal values, at the edges then. So we have an identity between the maximum of the function and the maximum of the corresponding nodal values, both on the full domain and also at the corresponding part of the Dirichlet boundary. For a quadratic, that would not be the case. You can have a quadratic, of course, which, so to speak, is very simple. You just take a quadratic which is 0 at both nodes, but nevertheless it's negative. So you cannot assure, or you can also take the values a little bit positive, and then it's still possible that it goes through the negative part. So you cannot relate the extrema at the nodes to the extrema of the full function. But in the linear case, this is possible. Okay, and therefore we can then now rephrase our maximum principle, which is purely algebraic, so which deals with these quantities in terms of this quantity. So to put it together, we have now proven if we have a triangulation, so this is now really a purely qualitative statement. It's really for one fixed triangulation. If we have a triangulation which fulfills the angle condition in the sense described and fulfills the connectivity condition, then if we have to look at the finite element solution, if we have a right-hand side which is non-positive, then we have the maximum principle in the sense that the maximum at the full domain can be estimated by the maximum at the Dirichlet boundary here. The question is, is this possible to generalize? So this is now very specific. This is really back to the roots. This is Poisson equations in 2D. The only generality which we have is this unstructured triangulation, which is reflected in this requirement in the angle condition, basically. So what would be the situation if we have a general scalar, let's say scalar coefficient k here? This is not so clear to say. Of course, we can formulate conditions, but then it's not just a geometric condition, it's a condition which mixes up geometry and requirements on the coefficient. Or you can also put it in another way, if you know a little bit about, say, differential geometry or so, you could say, actually what we have to do is we have, so to speak, a new geometry defined by this k, and we have to formulate it in this geometry. If you think along this line furthermore, you could say our V ellipticity requirement basically says we can allow for variable coefficients, but in the end it should not vary too much from the Poisson situation, from the constant one or situation in the coefficient. Let's see what this means if, for example, this is a quite typical situation, the diffusion coefficient is element-wise constant. This is, for practical reasons, that's not a very big restriction. We would like to have, of course, we would like to have varying coefficients, we would like to have inhomogeneous material, but this everybody would accept as a good approximation, I would say. And if we do the same procedure as we did, computing these two ingredients of the matrix, then we see we get now this formula, because now we get this constant here in front of the integral. And you see here now, to assure a sign, we have an interplay between these. So we can allow here, so it depends now also on the size of these values, whether how the whole sum here behaves. And of course, it gets even more complicated if the whole thing is not scalar valued, but matrix valued, but because this means we not only have a sign in the values, but we also have a change in the values, we also have a change in orientation. So to speak, the rotating part of the matrix A, it's a positive definite matrix, so we can think of this matrix as having a rotating part and having a stretching part, and the rotating part then also changes the geometry. Okay, it's a little bit simpler to include lower order terms, to include diffusive terms or to include reactive terms. Reactive terms are no problem whatsoever, at least under one condition, namely if we will see this later on what this means. This is the notion of mass lumping. It means that we do not evaluate the integral exactly, even if we could it, but we use a quadrature rule for this part of the matrix, which then leads to a diagonal matrix for the approximation of this part. But if the R, the coefficient, is then non-negative, of course, the diagonal elements are also non-negative, so this only enhances the non-negativity, the sign condition which we have here. So this is no problem. So if the reactive part is discretized in a diagonal fashion, then there are no problems connected with this situation here. And it also, in terms of modeling, it also makes sense to do this mass lumping, because a reactive part means that it's really something which takes place at one point. There's no neighboring interaction as we have it with diffusion or convection. A reaction is really at one point. Reactants are there, and then there's reaction. And what is in the vicinity doesn't play a role. And if we would discretize with a matrix which is non-diagonal, we would bring in some sense artificial neighboring relation. So this is no problem, and with the convective part we have seen already that we have different ways to discretize the convective part. If we do it in the usual fashion, that brings in terms which affect the sign. We have discussed this with the finite differences and have seen if we really still want to keep the sign condition, that means that we get a condition on the Cell-Peclet number, telling us that the discretization has to be fine enough to maintain the M-matrix property. And similar things are here, and we also have seen the remedy of the upwinding technique, which then keeps the M-matrix property but reduces the order of convergence. So these things are very similar here in the finite element context. Okay, so it's Christmas, and that means The rest of the time till Christmas, we will relax. And that means that we do now something simple. So I will skip this section about grid generation a posteriori error estimates. Maybe that's a little bit too advanced for an introductory course, and I come to some basic things, namely the question, going back, the question how to solve the emerging linear sets of equations. So this is, I'm not going to ask you what you know already about that. Of course, you will tell me you know nothing about that. And I'm sure you know already something about it, so it will be a repetition to a large extent, but okay, maybe that's also nice. Okay, what we are going to do, we are looking again at a set of equations, ax equals b. Now the capital M is a small m to simplify a little bit the notation. And the emphasis now, of course, is to see what we can do if the matrix A is on the one hand side large, but on the other hand densely populated, where we still have to formulate what this really means. So we would like to use the structure of Ax equal to b. So we want to go away from direct solvers. Maybe later on we can discuss again the relationship between direct and iterative solvers. So this is very much intertwined also with the computer architecture which is available and with the storage which is available. And now for the last, how many, 20, 30 years or so, of course everybody thought that iterative solvers are the method of choice. And in this sense, we will discuss it here. But actually, there are also now some people which say we have a new advent of the direct solvers in the sense that we have no limitations with storage space anymore. The problem a little bit is, of course, also the storage space in the sense of the matrix is really extreme. That one is not even able to store the matrix with all the possible fill-in. But we go a step back and we say, okay, we are now looking at iterative methods and what is the best possible there. Okay, an iterative method, as you know, and as you will see again, is a matrix which is based on matrix vector multiplications with matrices which are derived from the matrix A in a sense that they more or less keep the sparsity pattern. So we only so we can say that the matrix, that is so to speak also our notation of a sparsely populated matrix. We will assume that the matrix vector multiplication with these type of matrices we are looking at is of the order of m, not of m squared. This means that independent of the m, we have an upper bound for the number of elements in each row which are non-zero. And that is the typical situation which we have in our discretization matrix. In the 5-point stencil, we got a matrix which, independent of the amount of nodes which we had, always had only up to 5 entries per row. And similarly, in all the other discretization, because this is then controlled over the neighbors, and we had conditions which basically said the amount of neighbors is limited independent of the size of the discretization. So this is our, so to speak, this is our definition of sparsity in a strong sense. And we're dealing about iterative methods. That is, we are dealing about a procedure which defines a sequence of iteratives, xk, on the basis of some starting vector x0, which then hopefully converges to the solution x of the set of equations. So we will assume that A is non-singular. So we're talking about a unique solution of this square problem here. And of course, there are the two ingredients which determine whether a method is good or not. The one is, of course, it has to converge. We have to have an estimate or some notion about the speed of convergence. We'll come to that. And of course, we have the amount of work we need for one iteration should be corresponding. So the overall amount is then determined by the amount of work we need for one iteration times the number of iteration which we need. So as we never can compute the exact limit, we have to have a stopping criteria, and usually it's formulated in this way, that we define a certain error level epsilon, and we want to reduce the error relative to the initial error to this error level epsilon. So what could be epsilon? In a naive way, we would say, okay, epsilon should be something like machine precision, or something in this range, or half of machine precision, or whatever you would like to have. A little bit more, a little more precise would be, we will see this later in more advanced methods, be to say, okay, actually we are not really interested in solving the system of equations AX equals to B, because this is just only an approximation for the underlying continuous model which we really would like to solve. So if we have some idea, and we have some idea, but unfortunately not quantitatively, about the error which we have between the continuous model and the discrete model, it's then sufficient to solve the discrete model also up to this precision. Otherwise, we would oversolve the discrete model. It would be not wrong, but it would be an unnecessary waste of effort. So, but at the moment, we just look at this quantity at some fixed quantities, and it either appears in our estimates or it just vanishes in the capital O terms. So we are in the following, we are very much in estimating the effort in M, because we would like to see what happens if M goes to infinity. The most simple methods, which I'm absolutely sure everybody of you knows, are the so-called linear stationary methods, which I will remind you. And then later on we will discuss a little bit, which you also should know, and also know gradient and conjugate gradient methods. And then a little bit more advanced things in this direction, where we'll end with a discussion of multigrid methods and nested iterations. That is the program. So let's start with a simple thing. A linear stationary iteration method is based on an iteration function of affine type, which has this structure, a matrix M, the iteration matrix X, plus NB. B is then the right-hand side. And a method is, so to speak, defined if I fix matrix M and N, in the sense then what I'm going to do is just a fixed point iteration. So I have my kth iterative, I plug it in here, so I have a matrix times vector plus vector to compute, and then I get my new iteration here. Now, of course, there are two requirements. The whole thing should converge. Now I would say, okay, fine, I take M equal to 0. It converges very, very fast. But then I have omitted another slight requirement, namely the solution has to do something with the thing which I want to solve. So what we would like to have, and that is the notion of consistency with a set of equations, we would like to have that the set of equations fulfills this relation. Why this relation? If we assume that this sequence converges, then phi xk converges to, then xk converges to x. Phi xk, phi is a continuous function, converges to phi of x. Xk plus 1 also converges to x. So in the limit, necessarily as a consequence of convergence, I have the relation x equals mx plus nb. So this is a fixed point relation which the converged solution of this iteration necessarily fulfills. And what I would like to have, this is a little bit counterintuitive because actually one would like to have it the other way, but we will see how the connection is, that any solution, or that our solution is only one, according to our assumptions, of the set of equations is also a fixed point. So the solution is a to the minus 1b, and so you see here, this I've plugged in here in this fixed point relation. X equals mx plus nb, and the x is a to the minus 1b. So this is a requirement for every b, for every right-hand side. So we don't want to have convergence results which are dependent on the right-hand side. And that means this is a matrix requirement saying a to the minus 1 ma to the minus 1 plus equals ma to the minus 1 plus n, or who is this? Okay, that's now very brief. Or a more convenient way would then be to multiply this with a to the minus 1, and then the relationship is identity from the right-hand side is then multiply the relation from the right by a to the minus 1, then we get identity equals m plus na. Maybe I write this down. So that is the notion of consistency. That is how these two matrices have to belong together and how they relate to the matrix A. So consistency is equivalent with the identity is m plus na. Okay. Actually, if the matrix N is invertible, in all our cases the matrix N will be invertible, then also the other direction holds true. So what we have seen now, consistency is a requirement which tells us a solution. We have now x solves ax equals b, and then by consistency we have x is equals to, what was the requirement, mx plus nb. Okay. But on the other hand, if we have this situation, my claim is if I have consistency of this situation plus n is invertible, then I also have x solves ax equals b. Why? So under this condition, actually, this is really the set of solutions, the one element set of solutions, either of the fixed point equation or of the set of equations is the same. Why? I plug in here what I have by my consistency conditions, mx plus nax. On the other hand, I have mx plus nb, and then you see, oops, it's really the set of equations. Okay, so this is the framework in which we work. This tells us what we are doing has something to do with the set of equations. And now, of course, we want to have convergence. And now I hope at least that you know that such a fixed point iteration is convergent if and only if, in a global and linear manner. What this mean, I explain in a second. If the spectral radius of M, so the maximum of the moduli of the eigenvalues, the spectral radius of M is less than 1. So this should have been a basic result in your introductory numerics course. So what means global convergence? That means the convergence independent of the chosen starting vector. We have convergence for every starting vector. And linear convergence means, maybe I write this down. Global I think I don't have to write down. And linear convergence means if there is a norm, which I may be not able to specify, if there is a norm on, Rm, such that measured in this norm, oh, it doesn't matter. Measured in this norm, the error between the exact solution and the iterative can be estimated by some constant, let's call it rho, times the old error. So this rho is, of course, to be a number less than 1. That means there's a guarantee that in this maybe unknown norm, there's a reduction of the error in each step by the factor rho. And of course, then you see immediately you can estimate the error at the kth level by rho to the k times the initial error, and you see this is then the type of convergence. Of course, it becomes critical. So this is the number we would like to estimate. And of course, it becomes critical if this number is close to 1. Rho equals 1/2 is a nice number, but rho equals to 0.99999 and so on is then not so nice. And it's even, and if we run into the situation, that by increasing the m, the rho becomes worse, then things become critical. Okay. Then you hopefully also know that if this is the case, then there exists a matrix norm, and that is the reason for this linear convergence. There exists a matrix norm, which is also a matrix norm induced by some vector norm, such that this matrix norm is also less than 1. If we have this situation, where is it? There's a little bit, not very much on these transparencies, but anyway, how is it? Let's assume consistency in the following. So then we have by definition xk plus 1 equals mxk plus nb. And we also have, as a consequence of consistency, the exact solution fulfills the same fixed point, the corresponding fixed point. So if I now define an error vector, which is just this vector which appears here, that is just the deviation between the iterative and the exact solution, then I can conclude for the error vector the relation, I just subtract these two relations, ek plus 1 equals mek. So I get this error equation. And now, of course, I can, and now I come to a proof of this situation here, I can estimate the error norm, the vector norm of E by, if this is induced norm, which I have on M, or compatible would also be okay for this step, norm of M times norm of Ek. And if I'm now in a situation, if this is my rho less than 1, then this is exactly my contraction factor, as it is called. So I'm done if I find, I'm done, and I'm also, so to speak, qualitatively done if I find a matrix, a norm, such that the induced matrix norm or compatible matrix norm fulfills this requirement here. And then I know this norm of M is the contraction factor in the sense of this definition. So our aim is now to estimate contraction factors. Okay, of course we need a stopping criteria for the iteration. And yeah, what can we do? Of course we cannot compare the solution with the exact solution because we don't know the exact solution, a part of exercises. Okay, so we have to look at something different, namely at the residuum. So we have to see how good does the approximate solution fulfill the set of equations which is supposed to fulfill. So if it would be the exact solution, there would be a 0 here. In general, this is a non-zero vector. We call this vector gk. G like gradient, y gradient, you either know or you will see later on if we discuss the gradient method. And our stopping criteria is to say this residuum should be, so this is, so to speak, the way how to realize residuum equal to 0. We require that the residuum, the relative residuum lies below a certain threshold. And here again, now of course the question appears: how does this criterion relate to what we actually would like to have? Where is it? Actually, we would like to have this here. Can we guarantee this relation without knowing the x, of course, on the basis of such a relation? And the answer will be yes, in principle, if the problem is well behaved, if the condition number is well behaved. So if it's a stable problem to solve this set of equations, otherwise it becomes critical. You always have to distinguish between the stability of the problem you would like to solve. The problem is solve the set of equations. This has a certain stability in the sense if I disturb the right-hand side, or also if I disturb the right-hand side plus the matrix, what is the consequence of this perturbation on the solution, irrespective of any solution procedure? That is the stability of the method, and which is reflected in the condition number of the matrix. And then there is the stability of the algorithm, of course. You could have a stable problem, but you could be so intelligent in producing an unstable algorithm. For example, getting elimination processes by subtracting numbers which are close to each other and getting effects which then enhance the rounding errors and things like that. But of course, on the other hand, if you have an unstable problem, then things become complicated. Then you have to do something. In principle, an unstable problem is unsolvable, so you have to solve something different. But this is now not our issue here. Okay, so let's look at the things you know. You know the Jacobi method, or method of, what is it called? Simultaneous displacements, Gesamtschrittverfahren. The Jacobi method is, let's maybe start with this situation. So what you do with the Jacobi method, you select you write down all your equations. You select the diagonal part at one side and the off-diagonal parts at the other side. Then you divide by the diagonal elements. Of course, this requires that the diagonal element has to be non-zero. But under the assumption that our matrix is non-singular, we can always find a reordering of the rows and of the columns such that this requirement is fulfilled. So it's only so to speak, of matter of writing down the problem. And then we have a fixed point relation, xi equals, so to speak, the rest here, and we iterate over this fixed point relation. That is Jacobi. And what does this mean in our notation? If we use as a notation this additive subdivision, additive decomposition of a matrix, it has nothing to do with the LR, with the LR, respectively, LU decomposition, which you get from the Gaussian method. This is just writing down L, the lower part of the strict lower triangle of the matrix, the diagonal part, and the strict upper triangle here. These are just the exact ingredients of the matrix here meant. It's only for shorthand matrix notation. So what do we have? Here we have minus L, the lower part. Here we have minus R, the upper part, and we subdivide by the diagonal elements, so we multiply with the inverse of the diagonal. So this is our fixed point iteration, and this means our matrix N is d to the minus 1, and correspondingly, and we see this again here, our matrix M is minus d to the minus 1 L plus R. And if you check, then this consistency requirement is fulfilled. Maybe we can, it's reasonable to write, before going on, to write down another version of this method. In the consistency, under the consistency requirement, I can substitute the M here. I can substitute the M by the identity minus NA. So I get here xk minus N AXK minus B. This I had already, and this is the identity minus NA. This is the thing which I can write for the M. So what you see here, the residuum appears here again in this formulation. And if we say we use a new notation, delta k plus 1 or delta k, I'm not so sure, just for the increment. So actually, this is the thing we have to compute. If we have this increment, we have to add this vector to the old iterative, and then we have our new one. The increment is then either, delta k plus 1 equals n a to xk minus b, or if the n is invertible, which is the situation, and that is the way that we get a feeling what we have to do, and we define a matrix W as the inverse, we have then this situation. I have now lost a minus somewhere here. So what do we have to do? In each step, we have to solve a set of equations, which, of course, at the first glance sounds ridiculous, because that is what we want to do in the end. That it can only be senseful if to solve this set of equations is of lower complexity order than the original problem. And you see here we are now at the extreme. The extreme case is a diagonal matrix. It's just O over O of M operations by dividing through the diagonal elements. It's the most simple situation you would like to have. So, and that is, and you see here a specific structure, what comes up. You see the increment is computed by a set of equations, and the right-hand side is the negative residuum. Have you ever seen this again before? Have you heard of Newton's method? If you haven't heard of Newton's method, you should ask your money back from your numerics course, then it was rubbish, if you haven't heard of Newton's method. What is Newton's method? It is not our but is. So we have a function f from Rn to Rn, and we want to find a zero. So how do we do this with Newton's method? And this function is differentiable. Okay, I'll try to do it this way. Fill it in. If you don't know Newton's method, you don't know nothing about computing. You know, you're aware of that? Okay, let's derive it. So what do we do? The idea is very simple. We approximate, so to speak, this quantity. So this quantity should be 0. We approximate this quantity by a quantity which we know, because we know xk, plus the linear approximation. So what I have to write here now, times what in this notation with a delta? It's just the xk plus 1 minus xk plus delta xk. So this is the linear approximation which comes from differentiability. And now it goes on here. And if I cancel this part, then I solve this set of equations. That's it. So I solve Jacobi matrix of x at xk equals minus f on xk. That is Newton. And you see, it's exactly the same structure, minus the residuum at this side. And here, an approximation. Here, an approximation from nonlinear to linear. Here, an approximation from linear complicated to linear simple. By the way, what would it mean if you apply the Newton's method to, if the Newton's method is the method, why don't we apply the Newton's method here? Why don't we apply the Newton's method for ax minus b? What would it mean to apply the Newton's method to a linear problem? Let's write it down. What is this here? What is the Jacobian of this? I do not go further till I have heard an answer. What is the Jacobian of an affine linear function? I heard a very silent A. Okay. And what is our minus f? It's minus our residuum. Is this a reasonable method here? No, because it means we solve the set of equations by solving the set of equations. It's only a rewriting of the problem. It's also clear. This is approximation of nonlinear by linear. This is approximation, as I said, of linear complicated by linear simple. Okay. But the structure is absolutely the same. So the other method which you all know is the Gauss-Seidel method, the method of successive displacement. And the idea is, if I do this kind of iteration, then I have the idea that the k plus first iterative is already better than the kth, then of course I should use the k plus first as soon as I can. But if I go through the computation in this sequence, which is here indicated by 1 plus m, So this brings in a sequence in the computations. Here you see there is no sequence. I can do this also in parallel if I want. I can all these m steps in parallel, which is also a sort of advantage of the Jacobian method. But if I bring in this sequence here, could also go back or take another sequence, but if I take this sequence, then I would say, okay, here I know already the new iterative. Then I use it. So instead of the xk here, I have here the xk plus 1. And that is the Gauss-Seidel method. So plugging it in here, you see, it doesn't change the effort whatsoever, because in implementation, this just means I store the new iterative at the position of the old iterative from the moment on where I have it. And this automatically transforms this method to the Gauss-Seidel method. So it's exactly the same operation count. Also, it looks a little bit different now in theory if you look at that. So what have you done here? So this is the situation. Of course, we have to resolve this implicit part here. So we bring this minus t to the minus 1L to the other side. So actually what we are going to do, this is now not on the transparency. You see now the matrix n to the minus 1. The matrix W is now d to the minus 1 times L. The matrix n is now t to the minus 1 times L. So that means we have to solve a staggered set of equations, a triangular system, which we do by, it's a matrix L, so it's a lower triangular matrix, which we do by forward substitution. But the forward substitution is, so to speak, already built into this procedure here. And therefore, there is no further solution apart of this division by the diagonal elements. Okay, these would be the two very old methods. And yeah, what can we say about them? Not very much. One can use them for small problems, I would say. There are criteria which assure, so in principle everything is possible. We will have probably at the exercise sheet, we will have an example where small matrices where for the one method works, the other not, and for the other matrix the other way around. But these are quite artificial examples. Of course, we would expect that the Gauss-Seidel method is better. And it is better for reasonable matrices, but it's still not good enough. That is the overall situation. A criterion to ensure convergence of both methods is the Strong Row Sum Criterion, saying that the diagonal element in modulus is strictly greater than the sum of the moduli. And if you look at our discretization matrix, and you see we cannot satisfy that. We satisfy that for those rows where Dirichlet data are involved, but it would mean every node has a Dirichlet node in its neighborhood, which is, of course, ridiculous. It's a very crude, coarse discretization. So this is too strong, this requirement. There are further requirements which are now not cited. Basically, it says if the matrix is a positive result which is usable, basically says that is given here. If the matrix is symmetric and positive definite, that would apply in our case for the pure diffusive plus reactive case without convective forces. Then both methods converge globally. And the statement basically is that the Gauss-Seidel needs half of the iteration of the Jacobian, which sounds good, but it's not good enough. Okay, so let's see what we can do. And to do so, we speak about something very, very simple, which is related to the Jacobian. It's the Richardson iteration. If you would want to know more about the Richardson iteration, you have to come on Tuesday to the Christmas lecture. There it will also play a role. So the Richardson iteration is the simplest thing we can do. So what it does? It in this decomposition of the matrix of the matrix A, in the sense as we have it here, to produce the matrices M and N, we just use as the matrix N the identity. This ensures that we don't even have to divide by diagonal elements. It's the absolutely simplest situation for this auxiliary problem. So N equals W equals identity. And then necessarily, for consistency reason, the M has to be I minus A. So what we do is practically we have our fixed point, our set of equations, and we make a fixed point relation out of it by adding X, by adding identity times X on both sides. And over this fixed point formulation we now iterate. Okay, because this is such a simple method, we can also not expect that it converges. We have to look at the spectral radius of the matrix M. So we have to look at the modulus of, so the eigenvalues of 1, identity minus A are 1 minus the eigenvalues of A. So lambda of A denotes the eigenvalues of A, and lambda max denotes the biggest, and lambda min the smallest. So these two numbers are the candidates for the maximal eigenvalue. So, and of course, in general, this number will not be smaller than 1. If we now restrict ourselves to the situation that the matrix A is positive definite, then, okay, what can we then say more? Then we can say, okay, the eigenvalues of A are then real and positive. So the eigenvalues of M are also real. They are smaller than 1 because I have 1 minus something positive. But this does not prevent me from having the situation that I get negatives at eigenvalues below minus 1. So it also does not ensure convergence. And what we are going to do is we will do a new idea which is called relaxation. So, and we will see in the Richardson equation, if we do proper relaxation, we can bring the Richardson iteration to convergence. And relaxation means that we do not take as a new iterate that what would be given by the method, but we do, let's first say, a convex combination of this value and the old iterate. So that would correspond to this situation with an omega between 0 and 1. So on our way from xk to xk plus 1, we do not go the full way. That would be the situation omega less than 1. In terms of the Newton's method, that would correspond to the damped Newton method. We do not do the full correction, we only go part of the correction. But what is also included, this is under relaxation, but what is also included here is over relaxation, meaning omega can be bigger than 1. We go beyond the iterate. Okay. Okay, we have no time today more to discuss this a little bit, but next time on Tuesday we will see that, as I said, by doing this correctly we can make a non-convergent method converge. Okay, let's stop here.